Alright, so now let's talk about the immune system. Alright, first of all, what's immunity? Well, immunity is your resistance to disease. Awesome. Well, what does that mean? We're under constant attack by stuff. Bacteria, viruses, parasites. There's infinite numbers of infect you and kill you. But we're good. It's defense. Actually, there are two overlapping systems here. What's called the innate immunity, or the innate defense system, active. The innate form of this is often called non-specific, and adaptive is specific. So let's start by looking at the innate part. Now, innate means that you're born with it. You don't have to do anything. It's inherently there. And the first part of the innate system that you can think about is a physical barrier. It's the skin and the mucous membranes. Now remember we said that innate was non-specific, meaning that it doesn't matter what the infection is. Your skin is a physical barrier. It doesn't discriminate. It's not specifically looking for something to block. It's the barrier. The second part of the innate system are various chemicals and cells that help inhibit the spread of anything that would invade you. And it's going to include inflammation. So, chemicals here. The skin, slightly acidic. Does that kill stuff? It's irritating. There are lipids and sweat and oils that help repel bacteria. If we include the mucous membranes, in your digestive tract, mucus physically catches stuff. And if we're looking at like your stomach produces freaking hydrochloric acid. It's got a pH of, say, 1. Not a whole lot survives that acid bath. There are enzymes in tears and saliva. There are lots of chemicals that help, at the very least, inhibit the spread of microorganisms. Mucus is a great example of this because it does. And then that stuff is only being flushed in the back of your mouth, so you swallow it, and it takes that acid bath in your stomach and dies. There are also cells involved here in this innate immunity. These include cells that are what we call phagocytic cells. Phago is to eat. So phagocytic cells, they're big cells and they grab onto stuff and they eat it. This also includes what we call natural killer cells. Natural killer cells, what happens when you let Quentin Tarantino name cells. So We'll look at this in just a second, but this is also innate or non-specific immunity. One of the major mechanisms of non-specific immunity is inflammation. And all the inflammatory chemicals. There are also proteins in the blood that are antimicrobial, of course, things like fever. So let's start by looking at phagocytic cells. Phagocytic cells include macrophages. Macrophages used to be monocytes. Now remember that monocytes are one type of white blood cell. Leaves the bloodstream, and then it's just walking around. Eating stuff that doesn't need to be there. Neutrophils, look at another type of white blood cells. Neutrophils can also leave the bloodstream. And when they encounter that infection, usually bacteria, they will phagocytize that. Now, in order to make this happen, in order for this to work, this whole thing of phagocytosis, not magic. It's not Pac-Man either. In order for phagocytosis to work, this phagocyte, either the macrophage or the neutrophil or whatever, has to bind to this pathogen. How is this going to work? This is non-specific immunity. It's not out there looking for specific pathogens. Well, this works by something called opsonization. Opsonization facilitates phagocytosis because it marks a pathogen for that. It's like adding a tag to the cell that says, eat me. Got a bacteria wandering around. Opsonization is slapping a sign on it that says, this one needs to die. And opsonization can happen in different ways. We may use something called a complement protein, or it may involve antibodies. More on that later. But the phagocytic cell has to bind to the pathogen. It has to bind the receptors, grab that, and then it's going to pull it in through endocytosis and digest that. Once it's brought in, there are lysosomes and other chemicals inside there that are going to break it down and kill it. Now, a minute ago, I mentioned natural killer cells. So, not only are these the most badass named cells in the immune system, they kind of earned it. They're the honey badger of this whole thing. What they're going to kill is something that's not you. What is it? Is it you? No? Die. So, natural killer cells are going to target any cell lacks self antigen. So this self antigen marks the cell as yours. We talked about this when we talked about red blood cells and blood typing, right? Those antigens in the surface of your red blood cell mark them as your cells. Natural killer cells are looking for something that's not you, or something that's wrong. Natural killer cells may attack cancer cells. They may attack cells that are infected with a virus. They may attack foreign cells. Doesn't matter, they'll attack that. We'll talk about the mechanism, but they cause cells to die. They're hardcore. Like I said just a minute ago, the major mechanism of non-specific immunity is inflammation. And inflammation is triggered when tissues are infected. Now, what is inflammation? You've seen inflammation. What happens? Your hand swells up. But whatever, something's going to swell up. What would make it swell? Fluid. What's going to happen is when tissues are damaged, or when cells like macrophages recognize an infection, they cause the release of something called a cytokine. Cytokines promote inflammation. And there are chemicals that will cause this to happen. Histamine. Cells that are injured release chemicals that cause these cytokines to cause inflammation. Now, when that happens, is the blood vessel that goes to that area is going to dilate. You get more blood flow there. Now, like we just talked about in lymphatics, put more fluid there, the more blood flow goes there, you're pushing more out of the bloodstream. So we've got our capillary bed again expertly drawn. Professional. Perfect. Every time. So fluid getting pushed out, fluid getting pulled back in. Well, inflammation happens. This blood vessel gets bigger. So now there's more fluid going out, which is swelling. That is edema, the accumulation of fluid in between the cells. Where's this fluid going to go? Into the lymphatics. And it's going to wash these pieces of cells or infection. It's going to wash that back into the lymphatics and out of the tissue. It's rinsing cells and moving that stuff in there. Not only that, you're pushing out more fluid, and with that stuff in plasma proteins and nutrients and minerals and crap that you need to rebuild the damage. You have chemicals called interferons as well. Now, interferons are going to disrupt something's ability to reproduce. They interfere. So here's the analogy for interferon. Imagine that tonight your next door neighbor's car gets broken into. They break all the windows out, they steal everything out of the car. Tomorrow, you're gonna go get an alarm put on your car. That's the interferon. A cell that's infected with a virus because it looks like that. The cell gets infected with a virus. This cell releases an interferon. The interferon goes to the cell next door and says, hey, I've got a virus, protect yourself. So now when this virus is out here looking for another cell to infect, this cell blocks it. It produces things that block the entry of that virus. That's an interferon. It happened when a cell was infected with a virus. There are lots of cells that will produce interferons. The white blood cells, lymphocytes, fibroblasts, These interferons, more than this, are also going to activate phagocytosis. They can activate natural killer cells. They're antiviral. Now, complements are a different thing entirely. There's like, let's say, 20-ish proteins circulating in your blood. They're not doing anything. They're inactive. They're just hanging out. Well, how do they help you? Well, the complement proteins bind to something that doesn't belong and marks it to die. Opsonization. So complements are involved in opsonization. The complements, you have this really amazing chain reaction that's going to occur. And my analogy here, it's going to make perfect sense to some of you. For some of you, you're just not nerdy enough to get the analogy. So, do you remember Voltron? Even some of you are like, yeah, I saw that last week. Whatever, new Voltron, old Voltron, whatever. If you're not aware of the concept of Voltron, you've got these robot lions. And these robot lions come together into this big giant robot that fights stuff. Separately, they're just like kind of like metal lions or whatever, but together they're one big robot. Complements are like this. Separately, not doing a whole lot. They come together into this big complex that is going to attack and destroy microorganisms. So you get your bacterial cell, and you get what's called a membrane attack complex. So these complement proteins all come together, and they combine, and they form this big thing, and it drives a big freaking hole in the cell that it's attacking, and then the thing just explodes. Complement proteins. Now, we're not going to get into the depth of like. So we're not going to get into the complicated thing of how complements come together or any of this. Just realize they exist. All of these things that we've talked about so far, non-specific immunity, innate immunity, they're also localized responses. And that's how, for the most part, non-specific immunity works. The exception to that is, of course, a fever. And a fever just raises it's a systemic response to infection. Fever is caused by a secretion from cells that are exposed to this attacking the body. The thing is called pyrogen. And it brings the resting body temperature up. And that elevated body temperature increases your metabolism, speeds up repair. It is antimicrobial, does help this. And there are benefits to having this moderate fever. Now, as you get higher fever, you may damage cells, and that becomes dangerous. But moderate fever is doing what it's supposed to do. Now, that's all non-specific, though. Like, it's not looking for anything, and that's not typically what we think of when we think of immunity. Normally, when we think of immunity, what we're thinking of is the adaptive response. This is specific, meaning that it is looking for a specific thing. It's not just looking for not you, it's looking for one thing. This is what we normally think of as immunity. It's specific, it's also systemic, which means it affects the whole body. It's not localized, and it has a memory. Now, here for our adaptive response, we have two parts. We have what's called, there are two parts here. We have humoral and cell-mediated. All right, so let's go with those things. First of all, again, just to review, an antigen, something your immune system can stick to. It's a molecule that the immune system can bind to. Something that can cause an immune response. Most of the time when we talk about antigens, what we mean is a non-self antigen. This is something that is not you. It's marked as not you. Now, all the cells in your body do have self-antigens, but normally when we say antigen, we're assuming you understand the immune system. Most of the antigens that we talk about will also be what we call complete antigens, meaning it has its ability to cause your immune system to react by itself. There are, however, things called incomplete antigens. And incomplete antigens are little tiny molecules that by themselves would not do anything. They become problematic when they attach to your proteins. The best example of this is poison ivy. So what happens when you touch poison ivy is a protein in that plant, or a chemical in that plant, binds to your skin cells. When your immune system is determining whether that's your cell or not your cell, well, now it doesn't look like yours anymore. So we get an immune response. You get itching and inflammation and redness and swelling because your immune system starts attacking. It does not think those cells belong there. Are they yours? Yes. Now they're yours with this additional chemical bound to them, and it confuses your immune system. That's an incomplete antigen. Something you should realize, though, is that when we look for antigens, when your immune system is looking for antigens, it's not looking for a big picture. It's looking for what's called a all right. So when you look at someone's face, you register the big picture, the whole face. That's that guy. Your immune system doesn't do that. When your immune system looks at an antigen, it doesn't register, there's that antigen. It registers individual features of the antigen. There's that guy with the giant nose. This is the specific part of the antigen that your immune system can bind to. And most complete antigens have numerous determinants. There's a figure in your notes that shows this antigen, these little puzzle piece sorts of determinants out the side. Your immune system's not looking for the whole picture. Your immune system's looking for that, the little things that it can see. Determinants, which means that there are multiple forms of defense that you have against an antigen. More on determinants later. And if you're following along in your presentation notes, diagram is the one that's got like red and blue puzzle pieces. Now, self-antigens are the things that mark your cells as yours. One of the more important self-antigens, the major histocompatibility complex, they're what mark your cells as your cells. We're not going to get into MHC proteins. MHC proteins take a protein from inside your cell, or a fragment of a protein from inside your cell, and hold it out so that your immune system recognizes it for you. But what we're really concerned with are these ideas of humoral and cell-mediated immunity. B cells and T cells. Let's start by talking about B cells. And if you're following along here, we're skipping through here, go pretty far. Where we're starting with humoral immunity responses. I love this slide. All right, humoral is antibody mediated. Oh, good. Antibody. All right, so here's how this works. You get an infection. This infection ends up in the lymphatics, right? It's going to be on that storm drain thing in those lymphatics. It's going to encounter a B cell. Now, what's going to happen? That B cell is going to bind to a determinant on that antigen. And it's going to bring it into the cell. Then that B cell is going to replicate. It's going to clone itself. And all those clones are going to have receptors for that determinant. These clone cells become plasma cells. Plasma cells make antibodies. In essence, this is the receptor molecule for that determinant. And those antibodies are going to go out and they're going to inhibit the way this antigen replicates or binds the cells, take it out of play. Some of the antibodies may mark the cells. The antigen for destruction, it's going to bind to it, it's going to prevent it from reacting. There are other cells that don't become plasma cells, they become memory cells. And the memory cells stay behind, and they're just prepared in case the same thing happens again. Now, this whole thing that happens, where you encounter the antigen, you activate the B cells, you make some clone cells, you make some antibodies, it's called your primary response period. Primary response period sucks, actually. It takes 3 to 6 days before it actually starts producing notable antibodies, and you don't reach peak levels of antibodies till about 10 days, and it just drops off. That 3 to 6 days super sucks because you're sick. After that, you start getting better. Well, then what happens if you get the same infection again? What happens if you're re-exposed? If you're re-exposed, then we see what's called the secondary response. Now, you left those memory cells behind. They're primed, they're ready to go. Those things respond within hours. The antibody levels peak very quickly. They peak in about 2 days, and they're at higher levels than what they were before. The antibodies are also better at their job, and the levels stay high for weeks. You don't get sick. Response period. Now, there are different types of humoral immunity, active and passive. Active humoral immunity is when you make antibodies. The B cell encounters an antigen, and you make an antibody against it. Now, this can be because you got an infection, naturally acquired. You've caught that infection, now you have antibodies against it. Or it can be artificially acquired. Artificially acquired active humoral immunity is from a vaccination. What a vaccination does is it spares us the primary response period. Because, like I said, getting sick sucks. That's the primary response period. You're giving your immune system time to form these antibodies and to react. Screw that. Instead, what we do with a vaccine, take the determinants off the antigen. Remember I said your immune system doesn't recognize the big picture. It's not looking for measles virus. It's looking for tiny little features of those viruses, little proteins on the virus that it can stick to. So we take those stupid little proteins off and inject you with them. Now, the same thing happens. Your B cells bring it in, they make clone cells, make plasma cells, and memory cells. But you're not actually sick. I didn't inject you with measles. Just pieces of it. Now, if you ever encounter measles for real, your immune system's already made antibodies against it. You don't get sick. We get the secondary response period where it's primed and ready to go. Now, people who get, for instance, measles are more immune to measles than people who get vaccinated. True. But who the hell cares? Nobody's measuring how immune you are to something. Let's just not get measles. Let's do that. You don't get measles, I don't get measles. We're all happy. Some people, you'll hear this and they're like, well, I went and got my vaccination and it made me sick. Well, what you get is your immune system working. They're like, well, I got a fever after I got the vaccination. Okay, that's non-specific immunity working. Just injected you with a foreign protein. It's not infectious. Not really going to make you sick. It can't enter your cells and replicate and kill cells. It's just a foreign protein, but you still get that non-specific reaction. Sometimes will include a fever and you feeling like crap. That will go away quick. There's this thing now that exists with vaccines and the anti-vaccine movement, anti-vaxxers, if you will. The anti-vaccine movement is largely based on a misunderstanding of how your immune system works, and partially based on a fraudulent study that was published and retracted. Let's talk about that first. The fraudulent study was published by a guy named Andrew Wakefield. Dr. Wakefield, not Dr. Wakefield, actually, he's no longer a doctor. So, published a study that linked the measles vaccine specifically to the onset of autism. Screeching halt. Wait, what? So, vaccines come. Oh no. So they published this article, people freaked out, they stopped vaccinating their kids. But what they didn't tell you was that, one, Dr. Wakefield had a conflict of interest. he had developed a new measles vaccine to compete with the old one. Is there any reason to change it if it works? No. Why would I buy a new vaccine from you when the old one's fine? I wouldn't. 2, he made up the results. Other scientists tried to replicate his data, could not do it. Finally came out he didn't really have any data. He made it up. It was fraudulent. Oh, it was fraudulent. It got published. The press picked it up. Damage done. There's still a large contingency of people that think vaccines are linked to autism. Vaccines are not linked to autism. There is no data that shows us that vaccinations can lead to autism. So that out of the way. The next is a misconception. I don't want them to inject me with that disease. We don't do that. We don't inject you with the disease. Injecting you with, again, determinants that can cause the immune system to respond, but not actually infect you. The anti-vaccine crowd has had many arguments against it. One was a toxin, quote-unquote toxin, that was found in vaccines called thimerosal. Thimerosal had mercury in it. Preservative or adjuvant or something. I can't remember. This was their outcry here was based on a misunderstanding of how chemistry worked. About chemistry, that's table salt, right? Sodium chloride. Taken separately, that is a metal that will leap into flames if just sit it outside in the air, and that is a poisonous green gas that will burn your lungs. Together, they're salt. Thimerosal had mercury in it. Did that mean that it was just like free-floating silver liquid? No. Just like that's not sodium as a metal, that's not chlorine as a gas. When elements are in compounds, they're different than if they were pure elements. Regardless, they did this out of vaccines. Public outcry. Was it necessary? No. But still, there's a large component of people, or a large group of people that are against vaccines. Whether you think it's government mind control or I actually had a student several semesters ago that did believe that this was the government to control us. My argument for her was, why would they want to? If the government actually cared about you, you might have better health care. They don't care about you. Don't kid yourself. They have no interest in any sort of mind control through vaccines. Are there reactions to vaccines? Sometimes people have reactions to things that are in there because they're made with animal products. You'll know they'll ask you if you have an egg allergy or whatever allergy with some of them because you might have an allergic reaction. So there's always this, but the benefit from being vaccinated is much higher than the cost. We're looking for something called herd immunity. And herd immunity is when there's so many people that are immune to a disease that you can't catch it. So if you haven't been vaccinated for measles, but everybody else in the room has been, well, you can't get it from us because we've all been vaccinated. I keep mentioning measles because measles is so incredibly contagious and so incredibly life-threatening. Measles is not chickenpox. It is not a standard childhood disease. It will kill you. It will scar you and do damage to the system, the nervous system. Again, it is not something you want to have. This comes up now as we talk about different therapies for the current pandemic. One of them is using antibodies, or whether we even form antibodies against it. Whether we can get it the second time. If you don't make any antibodies against it, you could get it the second time. It's going to be very difficult to vaccinate against something that we don't make antibodies against. There's active humoral immunity. Now, passive humoral immunity means you don't actually make your own antibodies. Passive don't make antibodies, but you get them. So how does that happen? Well, naturally, this would happen because antibodies cross the placenta, or antibodies cross through breast milk. So the antibodies of the mother cross over to the child. Artificially, we can inject you with antibodies. The thing with both of these is that's great because you're immune to whatever this is right now, but it does wear off. If you have kids, you're probably familiar with a virus called RSV, RSV soup or so. You don't want your kid to get it. We actually have a shot for this. The RSV shot. It's not a vaccine. It is artificially acquired humoral immunity. So this passive humoral immunity, they're injecting them with antibodies, which fights the virus as long as it's in the system. But as soon as it's gone, your immune system never got exposed to it because you didn't get sick and you didn't get a real vaccine. There's passive humoral. There's a great chart, slideshow that shows these different. One other thing that I would mention about vaccination, it's not a new concept by any means. Even before we were vaccinating, like with injections, the idea of inoculating people against disease by exposing them to that disease is super old. George Washington inoculated troops against smallpox. And smallpox is a disease. And whatever Revolutionary War Continental Congress, I don't know, I slept in history. His superiors, the general public, did not want anything to do with this idea because his plan was to purposely expose his soldiers to the skin part of smallpox. And he did. They got sick. They didn't die because they built up antibodies against it before they were exposed to the respiratory part of it. That would have, but then, and I mean, this goes back there. Many other cases of these sorts of inoculations where people were purposely exposed. All right. So now back to this idea of artificially acquired passive humoral immunity, injecting you with. This is the greatest example of this because it involves all of this. And so this, I mention this now because this is a great tie-in with like sort of exam questions. So we live here. We have rattlesnakes. Rattlesnake. Rattlesnake, right? Aggressive snake, likes to rattle. Likes to bite you. Once you dead. If you get bitten by a rattlesnake, we do have a rattlesnake antivenom. Sometimes these are called antivenoms. Those workers are antivenin, antivenom. And what this is that we're injecting you with antibodies against that snake venom. Where did we get them? Well, in the case of a rattlesnake, what we do is we take snake venom, again, so snake venom, and we inject it into an animal. In this case, I think it's like a sheep or something. Super sucks to be the sheep, and the sheep's gonna get sick. And we do it again. Again. What's happening is we're not killing the sheep. We're injecting it with enough to activate its immune system. The sheep starts making antibodies against that venom. Then we harvest the serum there, and we get those antibodies out. And there you go. Now I inject you with antibodies, snake venom, and takes it out of play so that it can't hurt you. One side note, in the United States, rattlesnake antivenom is ridiculously expensive. It's like $100 in Mexico, $1,000 or better a vial here. The same thing would work with like Black Widow antivenom, which we don't use, or the other things. It's done similar, if I remember right. But at least with the antivenoms, I know that's the same. That would be artificially acquired passive humoral immunity. Right, so all this is humoral, antibody mediated. Antibodies are these proteins circulating in the blood. Again, they're secreted by plasma cells, and they will bind to an antigen that was originally detected by that B cell. Now, the antibody comes in different forms. There are IgM, so that's immunoglobulin M. Immunoglobulin M is first. It's going to cause agglutination. More on this in a minute. And it's going to activate those complement proteins, the Voltron thing. Immunoglobulin A. Immunoglobulin A is in mucus. We don't hear a whole lot about immunoglobulin A, but you should know that it's in mucus. Diagnostically, immunoglobulin M is important because it tells you that you have a current infection, a primary infection. So immunoglobulin M is associated with the primary response. Immunoglobulin D, we just don't care about. It's a surface receptor. Immunoglobulin G is what most of your antibodies are. This will be the secondary response. So immunoglobulin E is our last one. Immunoglobulin E is associated with allergic reaction. So immunoglobulin E, we don't care about. Immunoglobulin G is the most abundant antibody. It's what's really protecting you. It's a secondary response. It's the main antibody. Immunoglobulin E is involved in allergic reaction. The thing is that you can make billions of different antibodies. There really is sort of an infinite number of combinations that can happen here. We've got mutation, we've got reproduction that creates genetic variation. One of the other big pushes against vaccination was delay the vaccination. Delay the vaccination schedule so that you don't overwhelm the immune system. That is not a thing. You are currently dealing with an infinite number of potential infectious organisms. There's an infinite number of bacteria, viruses, whatever, all this crap that's working against you, and you're still fighting it because There are like 25,000 different genes at least just dedicated to this, and those are constantly changing. So how does an antibody work? Antibody is going to bind to the antigen and disrupt it. They do something called neutralization. Neutralization is the simplest way this works. So if you imagine that you're a virus, viruses are really tiny. Here's the cell. Now, to get into the cell, you got to go through that cell membrane, right? Neutralization, that antibody attaches itself to the virus, and it's not getting through that cell membrane now. It blocks the site there. It gets in the freaking way. So now you've got a virus dragging around this big antibody. Yeah, it's not getting into a cell. It neutralizes. We may see agglutination. Agglutination is what we saw in the red blood cells, where we clump together things. So an antibody binds to the determinant. It sticks to a bunch of antigens and sticks them together. And just like before, if you've got a bunch of crap stuck to you, you're not getting into that cell membrane. We clump things together. Precipitation is a similar idea. Precipitation is when molecules that dissolve in the blood, soluble molecules, get linked together so that they're not soluble anymore, and they settle out. Then we have complement fixation. Where we activate that whole Voltron complement thing. We mark that cell for death. Cause the complement to bind to it, which marks it for death, or we cause that big membrane attack complex to form, and it causes it to explode. All right. That's all humoral immunity. Our other type of immunity is cell-mediated immunity. Now, humoral immunity, B cells, cell-mediated immunity, T cells. All this junk that we talked about with humoral immunity, and these antibodies and these B cells, antibodies, junk is extracellular. Meaning it's looking for something outside the cells, not T cells. T cells are after an intracellular antigen. T cells are looking for. How does this work? Does it go in your cell? Does it clean it out? No. T cells attack your cells. Just your cells that are infected. Your cells where there's something wrong with it. Sorry about that screen flash. Sorry about all that. I had to go feed my vegetarian dog. I wish I was kidding. More on that later. When we get to digestion and how that works and why my dog's a vegetarian. So you're thinking about actually bringing the dog to class during the fall semester. Wicker gets away with it in micro. Why shouldn't I? Alright, so, cell-mediated immunity. Intracellular antigens. Antigens inside the cell. It's not going to go in your cell. This is going to attack your cells. Now, there are different types of T cells. There are helper T cells and cytotoxic T cells, and regulatory T cells and memory T cells. And this depends on the type of cell differentiation protein that would CD8 and CD4 cells. CD8 cells will become cytotoxic cells. CD4 cells will become helper T cells. We're not going to get into the depths of that. Kind of what we're going to do here is compare antibody-mediated and cell-mediated. Antibodies, very simple. Just block it. Get in the way. Stop it from actually getting into the cell. So antibodies are looking for something in the extracellular fluid or the extracellular environment, secretions or fluid or blood or lymph outside the cells. T cells respond only to an antigen on the surface of your body cells. It is looking for a cell that is infected by a virus or a bacteria or a cancer cell even, or foreign cells that are transplanted in you. Earlier we talked about that major histocompatibility complex for the MHC protein. It's going to take a protein from inside the cell and hold it out. Well, if your cell is infected, that MHC protein is going to hold out a protein from the virus, or a peptide, whatever, from the virus. And that gets recognized by T cells. T cells are pretty dangerous. Not that antibodies can't be. There are some issues with antibodies cross-reacting with T cells. We have to be very careful with T cells because they have to kill your cells, but specifically cells that are infected with a specific antigen. T cells have to simultaneously recognize what's not you and what's you. So they go through a selection process to make sure that that happens. Now, we're not going to get into how the MHC protein works, displayed on the surface of the cell, whether it's class 1 or class 2 MHC proteins. The thing with T cells is that T cells get the antigen presenting to them, binds to it, and we get what's called co-stimulation. T cells amplify their own response. Helper T. So you have a viral antigen that is brought to a helper T cell. The helper T cell makes clones of itself, and it goes and it activates toxic T cells. Things here are important. One, this relies on what's called an antigen-presenting cell. Or an APC. Most often these are dendritic cells. Remember, these are cells that you would find in organs. Now, you have a cat. Cats are psychopaths. They go around all the time. For instance, today, when I walked on my front porch, I was greeted by a gutted squirrel. Why? We feed him because he's a psychopath and he murders things. So he ripped the guts out of the squirrel and left its blowed out carcass on the doorstep. I don't know about the dead squirrel on my porch, but to draw the connection to these antigen presenting cells. So imagine that you're hanging out in your house and you've got this cat and it drops a mouse corpse at your feet. On one hand, you're grossed out. You're like, ooh, mouse. On the other hand, you're like, hey, we have mice. That's the antigen presenting cell. It's going to bind to this antigen. It's going to eat this antigen, but it's going to bring back a piece of it for the rest of your immune system. So your immune system is, hey, we have an infection. Thanks for killing that and all, but also thanks for telling us about it. That's the antigen presenting cell. That T cell binds to the antigen presenting cell, which is going to stimulate it. It's also going to release chemicals that trigger this proliferation of the T cell. These, again, would be cytokines or interleukins. And these chemicals stimulate T cells. And without that co-stimulation, the T cells are worthless. T cells have to be activated by these other cells and then stimulated by them as well. Just like B cells, we get a primary secondary response. It takes about a week for primary T cell response, and then those T cells need to freaking die. About a week after, they're going to start to die because they are hazardous. They are killing your cells. You don't need them to start killing off normal. An important chemical here is the cytokine. Cytokine causes the differentiation and amplification of this. These would include those interferons and these interleukins. The interleukins are released by T cells and cause some of this co-stimulation. Causes the T cells to divide faster. Helper T cells are super important for this. In fact, without the helper T cell, you don't have an immune response at all. They activate both the T cells and the B cells. Now, the B cells can activate on their own, but it works a lot better when a helper T cell does this. Once an antigen presenting cell brings that antigen to the helper T cell, it then turns around and activates both the T cells and the B cells and causes their proliferation. And without that, your immune system sucks, if it exists at all. So they are essential. Not only that, they cause those antigen presenting cells that actually brought them the chunk of the antigen should be sort of hyperactive. Go out and do it. You give the cat a treat, it brought you a mouse. Now, those cytotoxic T cells, like I said, are killing your cells. How do they do that? Well, they find a cell of your body that's infected with a virus or whatever, some sort of intracellular antigen. And they use something called a lethal hit, or back to this Pulp Fiction version of the immune system. It releases a chemical called a perforin. Sorry. Perforin perforates the cell. Little holes in the cell. It releases an enzyme called granzyme. Crosses into the other cell and causes it to cytotoxic T cell walks away. Giant fiery explosion behind it. It doesn't turn around. This is exactly the same mechanism a natural killer cell would use. Now, the difference between a natural killer cell and a cytotoxic T cell is a cytotoxic T cell is specific immunity. A cytotoxic T cell is looking for a cell infected with that specific antigen. Natural killer cells is just looking for something that's not right. So for a cytotoxic T cell, it has to have the major histocompatibility complex displaying that antigen. For a natural killer cell, if it doesn't have the major histocompatibility complex, screw it, kill it. If there's an antibody sent to it, cytotoxic T cell, that's not its job. Natural killer cells will kill that. Different surface marker. Cytotoxic T cell, again, not looking for that. Natural killer cell will kill that. So the natural killer cell, same mechanism, just much, much less specific. There are regulatory T cells that help regulate this, and they release inhibitory things that help prevent autoimmune issues. Now, if you're following along in the slideshow outline, there are organ grafts, and we're not going to get into grafting organs or even immunodeficiencies for that matter. What we're going to talk about, and like HIV/AIDS we'll talk about later, but we're going to talk about autoimmune issues, because this is actually a subject that's kind of personal, I suppose. My 9-year-old has rheumatoid arthritis, which is an autoimmune issue. And an autoimmune disease is when the immune system loses the ability to tell the difference between you and not you. How would that happen? Well, in some cases, you might produce an antibody against your own cells or against your own extracellular molecules, or you produce an antibody that looks like another chemical. There are types of thyroid issues where you produce an antibody against an infection, and just as a side note, that antibody looks a lot like thyroid stimulating hormone, so much so that it activates your thyroid gland. Or you, for whatever reason, your immune system decides to attack your pancreas, or the joints, neuromuscular junction. So there are multiple versions of so many autoimmune diseases. How does this happen? Well, more often than not, what happens is that a foreign antigen looks like your antigen. So if you're infected with this virus, you form antibodies or you form cytotoxic T cells against that antigen, but it's really, really close to your own antigen. And your immune system just confuses the two things. Then it attacks your cells, your tissues. Or your immune system doesn't keep up with the changes. A mutation happens, and the antigen changes. Or you touch poison ivy, and your immune system doesn't recognize yourself. Or like the immune system is exposed to something that it hasn't been exposed to before, like the brain. There's a blood-brain barrier there. There's a blood-testis barrier. Your sperm cells form long after your immune system forms. And should your immune system meet your sperm cells, it will kill them. It doesn't know they exist. Autoimmune diseases suck, and they're really hard to treat because quite often, and this is the case with rheumatoid arthritis, treatment of that involves suppressing the immune system. And while it's effective, it leaves you open for infection. And so when we talk about vaccinations, and you need to be vaccinated so you can protect the more vulnerable people in society, those are the people we're talking about. People that don't have a whole lot of immune system because of it's being suppressed or it's damaged. It doesn't work correctly. And with any autoimmune disease, and if you suffer from one of these, and this any sort of infection, puts your immune system in hyperdrive, and it makes that disease worse. So you try to avoid that if possible. Now, another sort of autoimmune issue that we have is the hypersensitivity. So hypersensitivity is an immune response to what is really not a threat. It's a threat. It's not. And this can be fatal. It can cause damages. And it may kill you. And there are different types of hypersensitivities. The most well-known hypersensitivity is the acute hypersensitivity, or type 1. That's an allergy. Well, it's done by a bee. The bee injected with venom. Your immune system responds. Primary response period. You make memory cells. Now you're sensitized. You get stung by another bee. Now your immune system's ready to go. And interleukin-4, secreted by those T cells, stimulates the B cells and plasma cells to make antibodies, and this time it's immunoglobulin E. This mass of immunoglobulin E causes the release of histamine. Mast cells and basophils, and your blood vessels dilate, and you get this inflammatory airway slammed shut. Blood vessels dilate, so you get swelling, edema, peripheral edema. And we enter anaphylaxis. Anaphylactic shock, systemic response to an allergen that enters the blood. Either you inhaled it, or you ingested it, or you got stung by it. That allergen enters the bloodstream, and your immune system drops that immunoglobulin E in and freaking histamine. Systemic histamine release. Your airway slams shut. Fluid leaves the bloodstream and goes out into the extremities so that you swell up. And in doing so, your blood pressure plummets. And this may cause you to die. Treatment for this is epinephrine. Get somebody with that EpiPen. So remember what the sympathetic nervous system does. It reroutes blood to the heart and to the muscle. So those blood vessels in the extremities that have dilated, they squeeze shut. The airway opens and relaxes. It is a fast response with that EpiPen. Again, this is a personal thing. I have a 6-year-old. This girl is allergic to cashews. He's allergic to cashews. He's allergic to cashews. Weird one. How we found this out was somehow he ate one as we were sitting in the other one's rheumatologist appointment. And then projectile vomiting, like the exorcist. And the anaphylaxis and EpiPen treatment subsequently. That EpiPen is not mild. It's a big freak needle. And they don't approve it. And there are other types of hypersensitivities. There are subacute hypersensitivities. And these may happen when antibodies are transferred through plasma. So you get a transfusion reaction. Or they transfuse blood into you, and the antibodies from the other blood affects your tissue. This may cause insoluble complexes to form, can't be cleared, you get inflammation and possibly death. Type 4 hypersensitivity is really slow. This is helper T cells. When cytotoxic T cells cause damage. When macrophages and cytotoxic T cells attack your cells. Now this is a term that you've probably heard recently in our current situation. This idea of what's called a cytokine storm. A cytokine storm is a systemic inflammation. It occurs when a ton of cytokines are released, and it triggers these macrophages and cytotoxic T cells to damage your tissue. Now, this is going to cause inflammation, but it's also going to damage the tissues, and it can cause organ failure, tissue failure, and you get sort of a positive feedback loop. And here, your immune system is hurting you. You get hyperinflammation. All right. So with that, we're going to end this sort of brief overview of the immune system. From here, the next lecture that you'll want is cardiovascular 1, cardiovascular 2, and those should be up later. So for this, I did the whole whiteboard thing just so I could synopsize this and you didn't hyper-focus on the minutia of the immune system outline that will be on your blackboard. So lymphatics and immunity will be one continuous slideshow on your blackboard, even though it's broken up here on YouTube. So check for those notes on your blackboard. I'm also going to go ahead and post the cardiovascular outlines on your blackboard. It will be a little later today before I get cardiovascular lectures up. And then your lab stuff will get posted shortly thereafter. So look for that shortly.